So today we're doing two main things. We are starting with looking at the end of chapter 8, continuing to look at the applications of integrals to probability and statistics. And then we're also going to do a little bit with the beginning of chapter 8, where we're looking at setting up what are called Riemann sums to approximate areas and volumes, and effectively, it's almost like magic, turning those Riemann sums into integrals. It only feels like magic, though. It can be made rigorous, but that's something that's an important skill to get out of this class. So, with the end of chapter 8, we need to start with the idea of something called a PDF. PDF stands for probability density function. We're looking at applications of integration to probability and statistics. If you are, for example, a computer engineer major, you will have to take a class called probability and statistics, maybe even next fall, or maybe the fall after that, probably taught by me, where you use probability density functions, PDFs, all the time. Even if that's not your major, it's possible you might need this class. In fact, I know a physics major who took it a year and a half ago and was very, very thankful because it helped her a ton in her thermodynamics class. Thermodynamics is very statistical in nature. Probability density function. And to motivate this, I'm actually going to look at the example in the book. And I very, very highly suggest that you carefully read through this example and study it. I'm going to hit the highlights here. We're looking at something called the US age distribution. Data have been gathered from 2016 in particular about the number of people in different age groups in the country. And based on these data, they were able to figure out that 25% of the population in 2016 was between the ages of 0 and 20, just born, and maybe, the second before their 20th birthday. About 27% were between the ages of 20 and 40. About another 27% were between the ages of 40 and 60. About 17% were between the ages of 60 and 80. And about 4% were between the ages of 80 and 100. From these data, a common thing to do is to make something called a histogram, a bar chart that looks like this, where, this is very important, the area of each bar gives you the percentage, not the height of the bar, but the area. That's very important to realize as you read this chapter and think about this and do problems and try to understand what's going on here. It's the area that gives you the percentage, not the height. The height, notice this vertical axis is labeled in kind of a strange way. It says fraction of population per year of age. That's a strange label. What does it mean? It means, for example, for those people that are between 0 and 20 years old, well, the height of that bar is halfway between 0.01 and 0.015. It would be 0.0125. That means for each year of age between 0 and 20, babies who are not yet 1 year old, 1-year-olds, 2-year-olds, 3-year-olds, 4-year-olds, 5-year-olds, etc., we are approximating 1.25% of the population is each one of those age ranges. Baby, that's not quite 1-year-old, 2-year-old, 3-year-olds. For example, about 1.25% of the population is 3-year-olds. About 1.25% of the population is 4-year-olds. About 1.25% of the population is 5-year-olds, etc. Is that exactly right? No, it's an approximation. It's a rough approximation based on how the data have been grouped here. And if you do multiply that height, 0.0125, times the base here, times 20, you do get the area, 0.25, representing 25% of the population is between 0 and 20 years old. Okay? So the area gives you the percentage, which means the labels on the vertical axis are a little strange. That's only one way to group the people, though, right? You could group the people instead of 20-year increments, you could do 10-year increments. And on the next page, they do that. Now we got data in 10-year increments. And instead of percentages that are close to, say, 25%, they're close to 12, 13, 14%. And you can see between the ages of 0 and 20, it's a little bit less uniform than the first graph made it seem. For the first graph that I showed you, between 0 and 20, the area was 0.25. These two areas sum to 0.25, but they don't equal 0.25. They're not equal to each other. Their average is half of 0.25. These two areas sum to 0.27. They're not equal to each other. Same with these two. These two sum to 0.17. 17% was between 60 and 80, and these two sum to 0.04. 4% was greater than 80 years old. But you're seeing more detailed in the histogram, a finer approximation, you might say, of what's going on in each age group. What's this curve that you see up at the top, kind of following the tops of these bars? That's an approximation to something called, well, the PDF, like I just mentioned a few minutes ago, the probability density function. It's an approximation for it. Probability density function, we're going to call it, in this example at least, little p of t, t for time, because, you know, age can be thought of as an amount of time that you live. The independent variable is not always called t. It could be called x, for example. There's two ways to interpret the meaning of this. Okay, well, although I have to write it in a different line. And both ways of interpreting it involve doing an integral. That's why this is in calculus 2, because it's related to integrals. You can think of it, first of all, in the simpler way as the fraction of the population, between age t equals a and t equals b as being given by the integral from a to b of this PDF, little p of t. That integral, if you've done your modeling well, is supposed to give you the fraction, the percentage of the population between age A and age B. Of course, A and B could be lots of different things. Analogous to how in these histograms, the areas give you the fraction of the population. For example, the area, this first bar here, right here being 0.12 means about 12% of the population is between the age of 0 and 10, just like you see in the table, about 12%. The area is the answer. That's why we integrate. The area is the answer. But there's a second way to interpret this integral. You could also think of this as a probability. That's why it's called the probability density function. It's the probability that a randomly chosen person from the population has age between t equals a and t equals b. The integral, the area, represents both. They're the same. That should be intuitive. If 12% of the population is between age 0 and age 10, that should be intuitive to also mean that if you pick somebody at random, everybody's standing in a gym somewhere, close your eyes, point at somebody, that there's about a 12% chance that you point at somebody who's between 0 and 10 years old, assuming, yes, babies are in the gym. Little kids. It should make some intuitive sense that these should be the same. And we think of them as decimals. We can convert those decimals to percent. So 0.12 is the same as 12%. That's the concept. But how do you actually work with it? Dealing with some crazy curve like this seems perhaps more complicated than it might be worth. I don't think I could find a formula for a curve like that very easily. I mean, I do know how actually, but it is actually a lot of work unless you program the computer to do it for you. Better, though less accurate, is to come up with what you might call a rough model for this histogram. And the model the book chooses, which I will now talk about, is this one. Assume the PDF is constant between age 0 and age 60, and a linear decreasing function between age 60 and beyond. Now, there's lots of ways this could be done. What the author chose to do here was to choose to make the constant value here be 0.0135. That was a choice. Is it the best choice? Not necessarily. However, once they made that choice, that completely determines what happens over here, because the area under this graph must equal 100% of the data, 100% of the population must be between age 0 and whatever this last age is. Now, notice that they don't quite get to 100 years old, even though there are people that live past 100 years old. And in fact, they look like they only get to maybe about 90 or something, even though plenty of people live past age 90. That's because this is an imperfect model. And we just have to live with it or improve it. I'm not saying it's the best model. I'm just saying it's an option. Let's see if we can figure out what the formula is for this. The book does that in their example. So this is for the example in the book. What's a formula for this PDF, this probability density function? It's a piecewise formula. Piecewise formulas are very, very useful, actually, especially in probability and statistics. They occur all the time, actually. No, you weren't done with piecewise formulas when you finished chapter 1 in Calc 1. They come up all the time in probability and statistics modeling. Almost every single example like this, in fact, typically is some sort of piecewise model. I mean, there are some that are not, and there are very famous ones that are not, in fact, but many, many of them are piecewise. Remember, it was a horizontal line, and the horizontal line was at 0.0135. If somebody's between 0 and 60 years of age. We're assuming for the people that are between 0 and 60 years of age, that for every year in there, babies up through their first birthday, 1-year-olds, 2-year-olds, 3-year-olds, etc., for every 1 year, that represents about 1.35% of the population. It's a very rough approximation. Don't worry about it. It's just what you got to do sometimes. But what goes here when t is bigger than 60? That's not so clear. Let's draw the PDF over here. We need the area under the entire PDF to equal 1. What's the area of that rectangle right there? Well, it's base times height. (60) times 0.0135, 0.81. This area equals 0.81. Which means this area of the triangle over here must equal 1 minus 0.81, 0.19. The areas have to add to 1, 100%. That area must be 0.19. Those two things have to add to 1. That's a key thing to realize. So we know the area of this triangle. We also know its height. It's 0.0135. We don't know its base. But I know the formula for the area of a triangle is 1/2 base times height. .0135 divided by 2 is 0.00675. So B is 0.19 divided by 0.00675. And that's about 28.148. Looks like it's 148 repeating probably, but I'll just leave it like this as an approximation. That's the base of that triangle, which means what? It means, according to this model, nobody lives past 88.148 years of age, right? You could call that the drop dead date. Okay, nobody lives past then. Okay, of course, people in real life do. This is a model. It's not completely accurate. Okay, so that's where the last value of t is, where the PDF is slightly positive, you might say. That's a very rough statement there. What's the formula for that line? I need it for the formula for the PDF, right? So I need to find its slope. The slope of this line rise over run, the rise is negative, it goes down by negative 0.0135, right? And the run is the value B, 28.148. The slope is, okay, that is coming out in scientific notation there. It's about negative, there should be a negative sign in there, negative 0.004796. I rounded more in the previous section to negative 0.00048, but I think I'd like to include more decimal spots. Right, on the calculator, this is 4.796 times 10 to the negative 4, which means you need to move the decimal point to the left 4 spots, which means you'd have 3 zeros in front of the 4. And yeah, we do need the negative sign. That's the slope of that line. So let's use that now for the formula. I could also use the fact that this point, whose coordinates are 60, 0.0135 is on that line. So turns out I can write the formula as negative 0.0004796 times, in parentheses, this is a little trick I'm going to show you here, t minus 60 plus 0.0135. That is the unsimplified formula for that line because it's got the right slope, negative 0.004796 coming from here. It's times t. So that is the slope. And it goes to the right point. When t is 60, that becomes 0, and you get 0 plus 0.0135. That's got to be the right one. I'm actually not even going to bother simplifying it. The book does simplify it. I'm not going to bother. There we go. Let's get this into Mathematica. One thing you should know about Mathematica for the test is how to define functions using underscores. square brackets, and equal signs. The colon is actually optional. I just like doing it for certain reasons I haven't explained. But you for sure need an equal sign. You can get a piecewise formula in here. If you go to the writing assistant here through the palettes menu and go to typesetting, there's a button right there, piecewise button, and it pops up here. Essentially just type it as you see it, though don't type the word if in there. 0.0135, tab over. 0 is less than or equal to t is less than or equal to 60. Oh, here's a little bit of Mathematica magic for you. I type a less than sign and an equal sign, and as I type a t, watch it morph into a less than or equal to. Fun, 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 right? You have to humor yourself somehow. Woohoo! Here we go. Do it again, it's so much fun. Boop. It just turns into a less than or equal to. And then the other one, I'll go ahead and type it as I wrote it by hand. And I just need a plain less than sign there and then a less than or equal to here. Okay, there it is. Now, I did approximations here. So when I integrate this, it's not going to give me exactly 1, but it should be very close. Integrating the PDF in general is supposed to give you 1, representing 100% of the population. Okay, it did round it to 1. If I had rounded this further to 88.15, as I did in the previous section, okay, it's still rounding it to 1. Oh, I'm surprised. Okay. Okay, there it's rounding, not as close to 1. If it were an exact form with fractions and not decimal approximations, it would be exactly 1. That's a property that PDFs have to have. They have to integrate to 1. That's a fundamental thing to know, by the way, when you read section 8.7. And when you do homework on section 8.7, the PDF has to integrate to 1. What's it good for? What's the PDF good for? I already told you one thing it's good for. Integrating the PDF gives you these quantities, which are the same thing. Fraction of the population between age A and B, which is the same as the probability that a randomly chosen person from the population is between age A and age B. For example, what if A is 51.7 and B is 63.9? What percentage of the population is between those ages? It's going to be the area under this graph between 51.7, which would be right around there, and 63.9, which is to the right of 60. You'd have to add up the area of a rectangle and the area of a trapezoid, actually. This is close to 12 years of age. 12 times 0.0135 is going to be in the ballpark of 15, 16, something. Maybe a little less because we're now also in this range where the graph is going down. 0.13, 0.14, 0.15, 0.16, 0.17, somewhere in there. There it is, 0.161. About 16.1% of the population is predicted to be between the ages 51.7 and 63.9. Thought of another way, if you pick somebody at random from the population, that's the chance that they're between those ages. Close to 1/6. It's like the roll of a die, actually. Is it completely accurate? I'm sure it's not super accurate. In fact, significant digit-wise, I'd for sure round to 16% and maybe even 20%. I don't know. Depends on how good your data is. How good your data are, I should say. Data is plural. integrating the PDF helps you answer either question. Something else the PDF does is it can help you find the average age. Also called the mean age. Can't just integrate the PDF itself, though. That doesn't make any sense. If I integrate the entire PDF over the entire domain, I just get one. One is not the average age. You do have to integrate over the entire domain, which for this problem, is approximately, again, 0 to 88.148. But you don't integrate just the PDF itself, you integrate T times the PDF. Why? The book does give an explanation in section 8.8. I don't have time for it today. It's related to what we're going to talk about with areas and volumes here in a little bit, something called a Riemann sum, approximation to an integral. The Riemann sum is supposed to be fairly intuitive, though it's not easy. But the Riemann sum leads you to the integral. At the moment, it's just kind of mysterious. This gives the mean age somehow. What is the mean age? Let's think intuitively. It's got to be between 0 and 88.148. Couldn't be bigger than 88.148 or less than 0. If the age only went up to 60 and stopped, since this part is uniform, a horizontal line, the average age of the people less than 60 would be 30, right? Halfway between 0 and 60. If it were a horizontal line the whole way to 88.148, the average age would be half of 88.148. 44.074. It's not a horizontal line over there. Now it's going downward. So in reality, the true answer should be between 30 and 8, half of this, between 30 and 44. And it is. Turns out to be about 37 something. Just having the computer do it for us. By the way, you should be able to do these calculations by hand, though they're not pleasant. Don't forget to put the extra t in here, t times that, and put a star for times. This is like 37 something. Yep, 37.4829. Probably too many significant digits. You'd probably want to round to 37.5 for sure, and maybe even 37. Okay, yeah, between 30 and 44, like I guessed. And even, in fact, about halfway between 30 and 44. That's just something I'm telling you. You're just trusting me there. I'm not explaining why that gives you the answer. It is in the reading in section 8.8. And again, they do give an explanation there. It's worth reading. I'm not sure that I'm even going to have time for that explanation on Wednesday. Something else that's important as you read through section 8.7 and work on homework problems is a related concept called a CDF. This is the PDF, probability density function. CDF stands for cumulative distribution function. What is it? CDF stands for cumulative distribution function. Called capital P of T. So I'll make a big P, maybe even make a line down here to emphasize it's a capital letter. When in this class, if we had lowercase and capital letters going together, little f and capital F? Fundamental theorem of calculus, capital F is an antiderivative of little f. Same thing happens here. See me there? I jumped. Same thing, I'm excited. Same thing happens here. Capital P is an antiderivative of little p. But before we can see that it is an antiderivative, we need to describe what it represents. It's accumulating probabilities. That's why it's called cumulative. In terms of fraction of the population, it can be interpreted as the fraction of the population, for our example of ages, of age less than or equal to t, whatever t happens to be. And that is the same as the probability that a randomly chosen person from this population probability that a randomly chosen person from this population has age less than or equal to t. And again, the age idea is really only relevant for this particular example. If our situation was not ages, but I think another example in the book is weights of fish. Then it'd be the fraction of the population with weight less than or equal to maybe x instead of t, or the probability that a randomly chosen fish has weight less than or equal to x. Because it can be interpreted as fractions or probabilities, it could be found by integrating the PDF. And that's why it's an antiderivative of the PDF. This is an integral of the PDF, little p. Leave some space. Once again, we're talking for this example. For this example, what is the lower limit of the integral? It's 0 because ages can't be less than 0. Ages can't be negative. If we were in a situation where we have a quantity that could be negative, then we want some negative number there, or perhaps even minus infinity. And in the general case, you do want to put a minus infinity there, and the book describes that. What do you want to put up here? Since there's an arbitrary t here and here and there, in fact, we want to put a t in the upper limit of the integral. We've done that before with speed and distance traveled and velocity and displacement. That's why this is going to be an antiderivative. Fundamental theorem of calculus. And if I put a t up there, put something different here, like a tau or something. Tau d tau. And yeah, the FTC would say the derivative of capital P of t equals little p of t, and make sure those variables match. I'm using t there, so I got to use t there. Capital P is an antiderivative of little p, and that's one of the main themes in the reading. And that's one of the main themes that comes up in the homework problems, is to realize this. So then you see the graphical relationships between these things. And what's this good for? Well, since it's an antiderivative of little p, it's good for evaluating these integrals. Also FTC, the integral of little f from a to b, a little p, excuse me, and here I'm using t, which is fine instead of tau, is capital P of b minus capital P of a. Also at the FTC. That's an FTC. So it's good for finding probabilities once you've got it. It's an antiderivative that we can use anytime we want it. What does it turn out to equal for this example? Have to integrate that. Ugh. Not so pleasant. Well, it's not terrible. Let's do it. Capital P of t, I guess, is going to be a piecewise function as well. When t is between 0 and 60, integrate that part, you'll get 0.0135 t plus c. Any c? Not any c. We want a particular value c. Does anybody have a guess as to what this c should be?
0.0135.
0.0135 is a guess. I'm glad you guessed it. But we actually want something different. We actually want it to be 0. We want c equals 0 since we want capital P of 0. Oops, where is it? We want capital P of 0 to be the integral of little p from 0 to 0, which is 0. Integrate any function from 0 to 0, you'll get 0. So this expression, no matter what it is, c has to be chosen to make this equal 0 when t is 0. So c must be 0. So it's capital P of 0 must equal 0 for this example. Not necessarily in general, this is for this example. Though there are many examples like this one. Oh, should I expand this out and to integrate? Actually, I can integrate it as it is. The second piece here. With the first part here, I could imagine letting w equals t minus 60, and then dw would be dt. I get a w squared over 2. Meaning I need to divide that by 2. Keep the negative sign there. Negative 0.0002398. And then I'll have a w squared, which means it's t minus 60 quantity squared. Integrate 0.0135, I'll get 0.0135 t plus c as well. But amazingly, it turns out this c can be 0 as well. But the reason's a little trickier. The reason that c can be 0 is because we want capital P of 60 to equal this area right there, the 0.81 area of this rectangle. Why did I pick 60? Well, partially because I knew the area of that rectangle is 0.81, and partially because if I plug in 60 right there, I get 0. 60 minus 60, 0. 0.0135 times 60, we already did that. 0.0135 times 60, that's the area of the rectangle, it's 0.81. It's already 0.81, so the c can be taken to be 0. Okay, check it if you're falling asleep. Check it after class. You'll see it works. This first case is if t is between 0 and 60. Second case is if t is between 60 and 88.148. Unfortunately, when I tried integrating this on Mathematica to confirm the formula for capital P, Mathematica wasn't doing it. Sometimes it seems like it does it, so I was a little confused. I tried doing this. Well, maybe if I do it as an indefinite interval, we'll do it. I think I did it as a definite interval before. Okay, yeah, that's better. This doesn't look the same as what I wrote, but it should simplify to the same thing. Tiny number there. It's writing it in kind of a strange way. Maybe if I expand. That's a little bit. You could confirm things. And here's our negative 0.000239. Just like I have there. In the last class, I used n integrate, but maybe I can do this. Maybe capital P of T. I just do percent sign, that refers to the preceding output. So I think that will do the formula for capital P. Maybe not. Okay. Maybe I can just copy and paste this. It's kind of weird that it puts true there. That true just kind of represents the other case when T is between 60 and 88.148. It's kind of a strange way to do it, but that's what it does represent. The main two cases are these last two cases. Now I can plot both functions together in the same set of axes, though if I do, the CDF goes a lot higher than the PDF does. Though you still can see them both. I'll make the PDF red and the CDF blue. Okay, so the PDF is down here, very low in value. It's horizontal and then it goes straight down toward the axis. It is the derivative of the CDF. It's telling you the slope of this line is 0.0135, and then the slope goes down towards 0. The derivative of the blue is the red. The integral of the red is the blue. The values of the blue are telling you areas under the red. And the blue's got to go up to 1, 100% of the data. Okay. So in the problems I assigned, they are some that are computational, some that are just purely conceptual. You need to understand these ideas. Reading will help. Studying will help.